So now we are going to talk about all this I said. Okay, we are going to talk about projective objects. And this is how we are going to connect it to finite dimensional algebras. Okay, so 5C. Okay, so first of all, so let me first do a few preliminaries in any abelian category just to remind everybody and sort of start slowly, if you will. These things are stuff you might have seen before, or some of you might not. So definition, an object. The first few things, the part 6, number 6, we will just do in abelian category. So an object in abelian category. Maybe I'll just say, let's say this is A, P in an abelian category. Let me give the abelian category a different name from change. A, okay, is projective. If for all objects M in A, sorry, if for all surjections or epimorphisms N to M, if for all N and so I need both I need both epimorphisms and both maps, I guess, right? Is this an epimorphism or a map? All these maps are in A. There exists an edge. So again, this is good topology. There is an edge from P to N, making the map, making the diagram coming. ये भी है ना? तो maybe I should skip the word maps. Should just. Okay. What diagram can you? Obvious diagram can you? There is an N here. There is M here. There is P here. This was F. This was G. Thanks. I'm not saying the H is unique. In fact, we will see that the H is not unique. Okay. Now that is one, and the second is you can similarly reverse the arrows, change the epimorphisms to inclusions. So reversing arrows. I won't ever use this again today, but this is a notion one uses. Reverse arrows and change epimorphisms, monomorphisms, meaning onto to into. We get to the notion of an injective or injective object. Yeah, we won't use it, but yeah, we get to this notion. Okay. Now, an abelian category is said to have enough projectives. We say A has enough projectives. Similarly, enough injectives, but I will not define that. If every object in A, so because of these all epimorphism, surjections, if every object in A, there is a surjection from some projective. If for all M in A, there exists there is a projective object P and an epimorphism from P to A, P to N in A. Everything is in this abelian category. So the goal of the, I mean, I will obviously sketch things. I'm not going to finish proving it. The first part of the talk and first part of this lecture is again the goal is to show the theorem. So we already know that the category O has, is abelian category. It is closed under taking submodules and quotient modules. It has a duality functor. It's a self-dual category. Duality is very nice. Duality helps us exactly go from projectives to injectives. So some of you might have learned to calculate, I don't know, cohomology or homology or extension X groups using injective modules, injective resolution. Well, you can do now go to projective resolutions using the duality. Or some of you prefer projectives, you can go to injectives using whatever. So duality, that functor is very useful. So now we know a bunch of nice things about category. Oh, it's finite length, it's closed under taking submodules. It has this duality functor. But not only that, you can talk about the category O, and it breaks up into these central character blocks. Each block has only finitely many simple objects in the twisted Y. And maps or extensions between different blocks are zero. Everything is direct sum. Right? So what we will show now is that the goal is to show or to sketch the proof of the fact that the category O or every block in category O has enough projectives. Okay? So O theta has enough projectives. So not only do there exist such modules inside category O, there exist a lot of them. For every object, you can surject onto it by one such. Enough projectives for all theta in X prime or W. Hence, so does O. Maybe I'll put it in a few parts. Let's do it. This is part one. Let's call it part one. Part two. Hence, so does O. Part three. I will explain why. Obviously. Part three, every projective has a finite filtration. And again, this, maybe I don't need to say this Varma flag business because I'll mention, well, maybe I'll mention. Every projective, it's the main theorem, so I may as well say it here. Every projective has a filtration, which is of course finite filtration, because anyway objects are finite length, whose subquotients by submodules, of course, whose subquotients. Finite filtration meaning this decreasing chain of submodules, the usual chain we have said, whose successive subquotients are one. These are the three parts of the theorem. So, okay, so we are going to get there. We start with some basic preliminaries on projective modules, and then in any abelian category again, and then ask to construct such a thing. So let's see. So because I need to at least know some basic properties of projectives. This definition is okay, but it's not very convenient. Let's start with some more convenient conditions. Okay, so this is all 6. So let's see. So maybe I'll call it 7. Basics on projection. Did anybody do this in like Amit's class or something? Anybody attended Amit Kuber's class or somebody else's projective resolution? Okay, this is maybe.
Sorry, Apoorva. Did you ask something? I'm here. Yeah.
Basics of projectives, like form is exact or X or whatever.
Oh yeah, I have done all those things. Yeah.
Oh, you have. Okay, thank you.
Yes. Yes. I thought you are just revising.
No, but I don't want. If you have done it, I will rather spend the time.
I have also done the definition of a projective cover, if you wish. Yeah.
Oh my God. Okay, that will come at
Yeah.
the end. So,
Okay.
let's write down the proposition which Amit has done. So I won't. The following are equivalent in an abelian category in A for an object P. The one, P is projective. 2, X. If you take X in this category from what? Let's see. Do I want X first or common first? X. X from P to whatever is 0 for all objects M in A. And the third is that the form, if you apply this form functor, right, the usual one, is exact. These three are equivalent. Amit has done this. Maybe if I have the mood, I will include the proof in the notes. But anyway, for now, this is good enough. The corollary, okay, Amit, you can tell me again. Have you proved that projectives are closed under direct sums and direct summands?
Can you please repeat? What did you ask?
I'll write the corollary and you tell me if you prove.
Projectives are closed under direct sums and summands. Yeah, I have done that. Yeah.
Wonderful. Thank you.
Yeah.
Another thing I need to do. Great. So say P equals P prime plus P double prime in A. Then P is projective if and only if P prime and P double prime. That's another thing that Amit has done. Yeah, fine. Great. Actually, that was it. So now let's put number 8 part. Okay, great. So this is the reminder. Maybe I should call it reminder because Amit has already done it in the schools. So now 8. How does one construct projectives actually? Right? So I have these three properties. So now what we are going to use, for example, is this. Well, clear. I will definitely use this. I might be using this as well. Okay. So let's see. So the entire thing. Okay. So I will not at all touch the part about part 3. So I'm not going to even touch why this happens. Okay. But maybe I will say the following. Let me get rid of part 2 and part 3 in this. Let me prove part 2 and 3 of the theorem in assuming part. So proof of theorem, proof sketch, obviously. Okay, just let me do part 2. Part 3 I will get to later on and again dispose of it at some point with not sketching, with sketching, with not even sketching. Right. So O theta has enough projectives. What does that mean? There exists by part 1. Okay. For every object M in O theta, so no, let's not say 5. I want to prove that there are enough projectives in O. So what does it mean? If we take any object in category, obviously non-zero. So if M is any projective subject onto 0, so oh. Is it clear now? Is it clear from this definition or in this definition that the 0 object is projective because everything is right? So of course M equal to 0 is projective. So of course it subjects onto itself. So say M is non-zero. Okay. Maybe I should not even have said that. I'm not thinking straight on the fact. Let's start with any object M in O. I want to show there is a projective subjecting onto it. Now let's look at the following. M first of all, by yesterday's lecture, theta in H star mod W is M theta. To write this down, there's some things, but each M theta belongs to the block 4. Now every block by part 1 has enough projectives. That means by part 1, But you can find the p theta. Okay, I should mention only finitely many are non-zero. But M has finite length. Everything has finite length. So only finitely many of these modules can be non-zero. Everything else must be zero. Now by part one, let's just say maybe theta 1 to theta n. Say m theta 1, m theta k are non-zero. Obviously, again, as I said, if the object itself is zero, then zero is projective, so that's fine. So let's say there are some non-zero, finitely many non-zero objects, some m's of n. Great. By part one, there are some projective modules. There exist projectives. There exist objects P1, Pk, Pi, Pj projective in category O block theta j, which subject onto each respective module mj. Fine. As a result of this, of course, you obviously have, if you look at the direct sum of the pj's, let's give this a name, P, subjects onto mj. Onto the direct sum of the m theta j's, which is this m. Because remember, m was the whole direct sum, but these were the only non-zero sums. So this is j equals 1. So P subjects on this, and of course P is an object of this. Each Pj belongs to this category O theta j, so P belongs to category O. So the only thing needed to show is P is projective in category O. And the reason for that is the claim that every Pj already is projective in category. And then by this corollary, so is the direct sum. So by 7b, enough to show each Pj, which is in O theta j, therefore it is in O, so it's an object of the bigger category O, is projective in O. Okay, and that is very easy for the following reason. Proof. I can use either this one or this one, either way. Let me use X. So X1 is all. So that's it. So given n in n, so let me not call n, n was already used. Given n in category O, we want to show that X is 0 between Pj to n. Let's write n as n theta j, n thetas as usual. But let me do the following. Let me take n theta j separately and the rest of them separately. Maybe I'll call this form is equal to n theta j plus n other things. Theta prime 1 plus n theta prime s. N theta j here can be 0. I'm not saying it cannot, it has to be non-zero. It could be 0, but I include that particular block nevertheless. And some other s many possible non-zero sums. There are only finitely many non-zero sums. Everything is finite length. So obviously, finite. Write this thing. And now just do this. Then the pen is now x1 category O of Pj and n theta j. How much is this? The claim is this is 0. Why is this 0? Because n theta j is in the block O theta j. Pj is projective in the block O theta j. So projective module means x is 0. By 7, 8. And I claim that if you look at any other x, x1 of Pj, n theta prime, whatever, L, theta. I claim this is also 0. Why is this 0? This is 0 because this guy belongs to one different block, O theta j, and this guy belongs to another different block, O theta prime. And all, as we saw yesterday, forms and x between objects of different central character blocks are 0. I don't even need to worry about whether this is projective or not. This is in different blocks, so it's 0. These two blocks are not equal there. So x12 from Pj to each individual factor is 0. Then using the long exact sequence of x inductively, you can build it up. So this again is the long exact sequence argument we have now seen at least I think 5 times. So I'm not going to repeat it a 6th time. By now you should be familiar enough using the long exact sequence of x's. X what this x0 is called form, x1 is x. We I should say using this inductively. We get what we for all objects n of category O. But then by the same proposition 72, that Pj is projective in O. So basically all we are saying is every object of projective in a subcategory, which is extension closed. Extensions to outside things are 0. It's projective in its own category. So extensions to inside things are 0. The extensions to all direct sums are 0, which means extensions. Pj is projective O for all j. Therefore, as I already said, by 7b, so is P. And so now every object M, you break up into its central character summands, you find these PJs subjecting onto them. Each of them is projective. So the sum is projective in category O and subjects onto this. So category O has enough projective. So it remains to show that every category O theta, central character block, has enough projective. Let's start by asking, does it even have one projective? So let's first of all get our hands on some actual projective. Okay. So let me do 2 examples, maybe. Yeah. Okay, let's do some examples. Fine. Okay, let me do one example in general and another example in SL2 and then get to the indecomposable projectives and so on. Okay. This is this. 8. 8 okay. 8 what was 8? 1 implies 2. 8 feet. Example of a projective. Over NEG. And the next one will be in SL2. Yeah, so let's see if I can actually get to proving part 1, how much of part 1 I can sketch. But if not, at least I've shown you that once you know part 1, projectives in a block, then you can easily just get the projectives and enough projectives in the whole category. Now let's see part A. So examples of projective, here is the idea. We have some blocks, it's a twisted while object. Right? And so that means you have some weights, dominant weight maybe, and some other weights. And some weights, this is lambda, this is maybe S, whatever. could be reflecting like this. So this is, I think, is cube of this. Well, this one, I have to tilt my head a little bit. Anyway, so there are some dot orbit of waves. So suppose so the point is here lambda is sort of maximal among all the other weights are less than that. So you can talk of the maximal weights inside this any crystal biology. Of course, obviously, if suppose the lambda was something like √3 times the fundamental weight, then when you do S1 of lambda, that is lambda minus some integer time. Sorry, it will be what? No, okay, even easier. Suppose lambda is √3 times the simple. Then what is S1 of lambda? S1 lambda is minus √3 times the simple, which is lambda minus 2 √3 alpha. This is not comparable to lambda because the difference is not an integer sum of simple. It's a positive sum of simple, but not an integer. This is not less than that in the partial order. So there will be some things that are not even comparable. There might be blocks where the highest weights are not comparable, but nevertheless, you can talk of all the maximal weights, okay, inside this block. So to say, maybe I should call it a lemma. Say theta equals W. So say mu is any maximum weight. Mu in W dot lambda is twisted by the theta is maximum. In the partial order. Maximum in or with respect to the partial order. Then I look at the Verma module, just a simple Verma module. That is projective. We already know that the Verma module mu will lie in this block because every simple quotient will have to come from highest weight from this twisted orbit because the central character comes by the same. O theta and hence in all of O by 7a. This is exactly what 7a was. That projective Pj. This should be one example of Pj. It's projective in the block and therefore is on. How does one prove this, right? So we have three ways of proving projective. I'm not proving the. Do I prove the lifting property? Suppose we can do this. Let's prove the lifting property for a change. So say n to m. So this is the Verma module mu in O theta. This was called F. This is called G. Right? Okay. Obviously, if m is the module 0, then I can just take, then this is the 0 map. So the 0 map factors to take mu to 0. If n is 0. Sorry, if not m is 0, but if the image, if g of m is 0. I don't care if the module is 0. I just care where the Verma module is. Then let h take the Verma module here, 0 in it. Clearly, take it to 0, 0 goes to 0, this goes to 0, we are done. Else, so this if then else, this is non-zero. If it is non-zero, it means that the generator must map to non-zero element here. Otherwise, if the generator maps to 0, then the whole thing maps. I'm trying to check. I'm not sure. I haven't worked this out, but I think I may have done this like 20 years back. Let's hope that argument still works, and then it should not be too hard to figure. Else, g of mu is non-zero. And of course, it's an element of mu. Oh, sorry. If this is equal to 0, then m itself was 0. Sorry, because it's a surjection. Anyway, but now the point is this is an mu. Fine. And this is a module map. So what does this mean? Also, mu subjects to M. Which means that M is a highest rate module of highest rate mu. Right? Okay. And we also know N subject. So let's see, that means that there is some vector here that subjects onto G of N. Choose choose, let's, I don't know what to say. So this is N mu belongs to N, well, belongs to F inverse of G of M mu. Right? Fine, great. Now let's look at the claim is that N mu itself is a maximum. So what should we be doing? Right? I want the map that goes from here to here. This is a Verma module. It's generated by one vector. This side. M. I never mentioned that M mu is the highest rate vector, but by now that is the concept. This is the highest rate non-zero, highest rate non-zero vector in the mu weight space. So what do I want to do? I want to obviously send that highest rate vector to this vector, and then it will just map here and then everything. What is the problem? There is no problem. What could be a problem? The problem could be, so we want to map this thing. So if what is this energy? So n plus times n mu, or basically ei times n mu equals 0. If this is identically 0, then we can do this map. Then this is the maximal vector. So mu goes there, ei goes to 0, and this is a free module. There are no additional relations here. That is what the universal property of the Verma module. Maybe I'll just say that. Then I wrote down that universal property by universal property of Verma module. That's what maybe actually then n mu is maximal. Therefore, by then n mu is maximal in n, which remember is an O theta, not just And so by universal, by universal property of the Verma module, and we could get the map. We could get H. The map H taking X times M mu. X is mu n minus because Verma module is like u n minus times the highest rate vector to X times n mu. This is the map H, and then of course this goes to this is map F X times F of n mu, which is X times G of n mu, and this will be G. This should work. So it suffices to check that this is true. Why is this? That is the whole question. And this is true because so far we have not made use of this assumption. The weight mu is maximum. But EI times n mu would belong to n mu plus alpha I. Okay, and look at the objects in this central character block. The simple quotients in these objects are inside this block, and mu is maximal. So none of those simple quotients have a weight bigger than mu because mu is maximal. This is the weight bigger than mu. This cannot occur in any simple quotient in the block. Therefore, it cannot occur in any object in the block. Jordan-Holder series and everything is semi-simple. So characters add up. So this cannot occur in the block. Therefore, but because n was in the block, so this must be 0. Since n is in O theta and mu is maximum in theta. That is why. That's it. That's why here. So the Verma module is present. Okay, now let's get to the other one. The other example is the same example that we have been talking about all these days. This was BC example in of a projective in the block with 0 and minus alpha. Remember the theta was the central character block of 0 and minus alpha over SL2. And it was exactly the same object. So okay, again, so in this projective block, clearly there are the weights are lambda equals 0, lambda equals minus alpha. These are the only two blocks. Weights S dot lambda equals lambda plus alpha. 0 is maximum because it's clearly minus alpha is a simple root more than minus alpha. So M0 is a projective. But there's also another projective. Remember that I said there are enough projectives in the block, which means over the simple module of this guy, M0 is projective, and guess what? It does surject onto the simple module. So this is the projective cover of the simple module. It is indecomposable, it's projective. What surjects onto this guy, which is L of minus alpha? Guess what? There is a projective module because that's what enough projectives mean. And the projective module that works is exactly our friend M2 comma. Remember we had this ML comma lambda. So it was M2 comma minus alpha, which is the quotient by E squared. This is the module that we have looked at. Remember, I'll just remind you, this is UG, quotient by UG squared plus UG times H minus alpha, H plus alpha. Because H is minus alpha. Claim is this is projective. Okay, so this is already 128. We have to learn 45. So let me not do any of these things. Now let me show you how to construct the projective in general. So the idea behind this guy, this E square business. Right? Let me show you what is the general principle behind it. I'm not proving this part. See? But so let me explain why at least I won't prove it's projective in the block. Well, maybe I will. Maybe I will. Okay, first of all, note. What was the composition? What was the filtration for this? We have seen the chain M of lambda plus alpha, which is this is M of 0 to M, which is M2 comma minus alpha, and then it subjects onto M of 0, M of minus alpha, M of lambda. I should use the other. So clearly now this part, so M0 and something is very wrong. M minus. These two objects belong to the same central character block. Therefore, this module belongs to a central character. So M2 comma minus alpha belongs to O theta 0. O theta 0 is, I could just call it O. This is the block theta. Okay. So it's enough to show that this is a projective. So to show it's projective, enough to show in the block, because if to show it's a projective in category O, in the big category, it's enough to show that the form in the block is exact, because we already saw that, right? That if it's projective in the block, then x between that and other things are 0. So we already saw why the theorem part 1 implies the theorem part 2. Okay. So more generally, I will not tell you how to construct the projective. I will outline it, but I won't write down the construction of the projective in full detail over a semi-simple algebra. But what I will write down basically as a special case. Okay. So, yeah, so I'm going to not prove it here. I'm going to prove this more generally. This was what number? 8C. No? Okay. So rise is to, more generally, we have. Now let me go back. This was, and this Verma module business was in all of every semi-simple year. This was over SL2. This Verma module is maximal weight, so fine. This Verma module is not a Verma module. This familiar object, this old friend of ours, is now I claim projective module when it already lies in the block. So it's enough to show this is exact. And I'm going to show this exactness for SL2 over a general semi-simple year. So now let's say back to G. Yeah. Given a lambda, let's do the following. Now let me get back to blueprint. So given a lambda, let's start, and an orbit. Sorry, theta is not belongs to theta. It belongs to h star mod. Yeah. Do the following. First of all, define. Define two things. We call it L lambda theta belongs. It's a positive integer. It's a positive integer. To be. I do the following. So I have some orbit, twisted right orbit, right? Mu s1 dot mu s2 dot mu. This is the orbit theta. I have some weight lambda somewhere. I look at all the elements in the orbit which are bigger than lambda. Bigger in the partial orbit. That means that element minus lambda is a sum of simple roots of a certain height. Remember I said I will use the height function. Now is the time to use the height function. Look at the maximum set height and add 1 to it. Okay. So L is 1 plus max height mu such that mu is in the central character block and mu is the equal. Look at all the elements bigger than lambda. See how much they are bigger by that height, add 1. So it's strictly bigger than all heights of elements above. Okay. That means, what does this mean? So if you take lambda plus alpha alpha I1 plus I1 plus alpha IL, L is L lambda theta. Let me call this equal to L. Then this is not less equals any mu in that okay. Because if it was less equals that mu, then the number of such roots you need to add is at most L minus 1, but I'm adding L roots, so it cannot be less. That is one. And the second thing I need to define is category O lambda theta. Again, full subcategory, of course. Full subcategory of all M in category O such that if I apply the raising operators n plus L many times, to M lambda. Okay. This is the construction that Bernstein, Gelfand, and Gelfand did, BGG did. Okay. And the claim is now that in this category, oh, and I forgot to define the module itself, and P lambda theta. Again, UG times 1 quotiented by summation I and I, HI minus lambda. So again, the image of 1 is going to have weight lambda plus UG times n plus to the L lambda. So I'm quotienting this out. The moment I quotient this out, what happens? What is the image of 1? it's exactly this weight vector weight lambda. And now I'm saying that that 1 is being killed. Sorry, n plus L theta times 1 is being killed, which means that this module is actually inside here. Okay. And so our familiar friend UG times E square, sorry, UG times H minus lambda of H minus whatever, H plus alpha of H plus UG times E square. Well, E square is the same as n plus square. So this is an example over SL2 of, sorry, this M2 comma minus alpha is an example of such a module for SL2 because it's exactly doing the same. UG times 1 quotiented by this plus this. Fine. So now we are going to claim. So first of all, so P lambda theta, you can check this belongs to O lambda. Okay. And applying UN minus at UH will only lower the weight. So only what applying UN plus does. And so yeah. The image of 1 is already killed and anything higher will be further killed. You can check this is true. And the claim is, so two claims. So claim, so will be proposition. One is that the P lambda theta is projective. So whether I should point out that O lambda theta, it is a set of all modules in O which have this property. This property, O is abelian category. It's closed under sub-modules and quotient modules. This property is also closed under sub-modules and quotient modules. This is abelian subgroup. So inside this abelian category, this object is projected. Second, P lambda theta has a Verma flag. Verma flag is just the filtration with sub-quotients as Verma modules. This was as in part 3 of the theorem. And this is how you actually end up proving that every projective object has a Verma filtration. It's because of this basic curve. You start all constructions with this, and from here you can deduce the other ones. So this is used in proving part 3. Okay. I'm not going to show you this guy, but this was basically just like what we said. So for example, maybe I'll do an example. But we already saw this. So for example, over SL3, suppose I'm quotienting by n plus square. Okay. That means I'm quotienting by, so what remains when you quotient by n plus square? What remains is the trivial word E alpha 1, E alpha 2. Now, if I do E alpha 1 square, that belongs to you, that goes away. E alpha 2 square, that belongs goes away. E alpha 1 plus E alpha 2. E alpha 1 plus alpha. That is inside n plus. It's not, it is also inside n plus 1 square, but n plus 1 square has 2 dimensions for this space. One of them doesn't die. So one of them. So now what might basically, basically what happens is you will end up doing something like this. You will, so for this one, you would get a filtration of the kind M. So basically, this should be something like M alpha 1 is alpha 2. Then this should be contained inside some M1, M2. This quotient will be M alpha 1, let's say. M3. This quotient will be M alpha 2. M4. This is M0. So something like this would give you something like this. Or if you want with lambda, then you would have prime lambda. Okay, so the point, and again, our old friend M2 comma minus alpha, or even ML comma minus alpha, had a filtration by Verma modules. That's exactly this is exactly the SL3 analog, and the claim is it was in general. So over SL3 was this example over SL2. Maybe I'll just write it above the SL was the ML comma lambda. That also had a SL2 filtration. Okay. So one shows that this is projective, and once you show this is projective, this is the prototype from where you get to all the other projective. Even showing this is projective is not too bad. This you show, maybe I'll just mention why. Since Hom from P lambda theta to M, Hom only in this category, in O lambda, not in all this category, only in this category, is precisely isomorphic to M lambda weight space. And obviously, if you take short exact sequence and compare characters, taking the weight space is the exact. The characters add up over short exact sequence. The dimensions of the weight space is that. So this functor is exact. Therefore, taking Hom from this is exact. Therefore, it's projective. That's how one shows. But again, it's not a very hard calculation. You can verify it. I'm just out of time. So I would like to end here for the main theorem that it has enough projectives. Okay. So now in the final whatever many minutes, that means this was 8. No? Okay. So this sort of ends the part of the main theorem. So yeah, maybe I'll just say that. This is the starting point. In showing the main theorem. Or in constructing, maybe I'll say in constructing. Then are we constructing projectives? Remember, we are constructing them in a central character block. Okay, so now the final stretch. So this is the end of the main theorem. This is 7, is it 8? 8. So now let's do 9, and now finally we connect to finite dimensional. Okay. So that is where the point of the that was where the point of the AIS was. Merge back. Okay. So again, let me start by writing down the main theorem. And then we will make some remarks about this theorem. I won't, of course, there's nothing to prove here. I'm just going to only make statements from now on, the last few minutes. So remember, category O was now, we started by this nice category O, but it's actually a direct sum of these blocks, which are closed under morphisms, meaning no Homs across blocks, and which are closed for objects, meaning no extensions. So this is like a self-contained category. We want to understand this category. The point is, each category, every block, is isomorphic or equivalent to the category of, to the abelian category, if you want, of finite dimensional modules, right modules, I guess, right modules over a finite dimensional associative. And finite dimensional associative C algebra, of course, everything is over complex numbers, which maybe I will denote by B theta. Okay, so that's the goal. I will just make some remarks now. Don't have any no more proofs. Okay. So the question is, how does one get there? Okay. The way one gets there is how to get to it. This is all that I want to talk about. It will take, as I said, 5 more minutes. Sorry, please bear with me, and we will end. So the idea is first we want to understand. So remember, every object of category O is a direct sum of some subobject. Now maybe that's not good enough. Maybe each object inside a block is further direct sum of something. So you can write down what was called indecomposables. So indecomposables are objects which don't further decompose as direct sums. So the theorem that one uses is called the Rule-Schmidt theorem. Which is that if an R module, so some and R is associative algebra or A module M satisfies ACC and DCC, ascending and descending chain condition, which by the Jordan-Holder theorem was saying that it is a finite length. Then it can uniquely then one has M equals M1 direct sum, M2 direct sum, K. And the summands are again unique up to ordering. All Mi non-zero, let's say R module M non-zero. All Mj non-zero are unique. Sorry, and all Mj non-zero are unique up to ordering and reordering. As a result of this, so one can talk about indecomposable projective. Oh, and they're called indecomposable. Called indecomposable. So you can talk about indecomposable projective module. You have a projective module in category O. As we said, if two modules are projective, the direct sum is projective. So maybe you start with the projective module, but it is not indecomposable. It is a direct sum. Then we said that every summand is also projective. So you can keep decomposing until you get to indecomposable. The projectives in this category O theta. Fact. These are in bijection. So as I said, now I'm not proving anything. I'll just write a few facts. Right? So fact. If you look at the indecomposable projective modules, how many are there? Are there infinitely many? Are there finitely many? Well, guess what? It turns out they are in bijection with the simple modules because you can actually construct a search onto map from each projective to simple. Right? Let me maybe denote the set of these guys as a P theta. Script, please, script. Okay. The size of P theta is exactly the size of the twisted value. There is no lambda. It's just the size of theta. There's a bijection. In fact, every object. And what does it mean? It means that since there exist these, there are enough projectives. So for every simple, there is a projective surjecting onto it. In fact, it turns out that there is this projective term. So each L lambda in theta is associated with this unique P, with a unique indecomposable projective. Maybe so I should call these. Let me call theta. Say theta equals lambda 1 through lambda s. We need to write it more precisely. So each L lambda I or lambda j is associated with unique indecomposable projective. Let's give that the name Pj belonging to this set of indecomposables with Pj is a projective surjects onto L lambda j, but it also in between surjects onto the Varma module. And that is clear because of the lifting property, right? The Varma module surjects onto L lambda j. I want Pj to be subject onto L lambda j because there are enough projectives. So this is the one surjective onto this object. Then by the projective property, it extends. And it has to subject because the highest weight vector has to be in the range, range. Okay. So finally, then we can write down the thing. So let me give you the Q, how to construct this algebra, right? So let Q be the direct sum of the projections. This PJ. 1, 2, what was it? Yes. This is now projective module because direct sums are projective module. It's an O theta and hence in category. Look at, so then B theta equals the endomorphism of theta is this form. Okay. And as we have already said, forms between objects of category or finite dimensional. So this is finite dimensional. And so one last point therefore is that just to mention the last item of this. So these are all facts. Maybe I should call them facts. This is B. So C. So what part C says that B implies. B implies that this becomes this. Let's denote this thing. So B implies that this set is non-empty. Okay, now B. These are the facts. 1, 2, 3, and 4. The final fact is that so now how do I go from this category to these modules, right? And I can just say it's equivalent, but it is nicer if I give you the equivalence. So the functor factors, maybe I should call this a theorem, right? This is really a theorem. Let me end by giving you the actual equivalence from our category O theta to the modules, right modules of this. Hom Q. So if you look at Hom in the block, this was the module Q. So this. Take the Hom functor. Because it is projective, we know that this functor is exact. And I hope equivalence of category is better than the exact functor, right? So this is an equivalence from, so this goes from the category of O theta to the, not to B mod, but to mod B. Finite dimensional modules over this algebra is an equivalence of categories, of abelian categories. With, I will leave one more line there. I can even give you the inverse equivalence. There is equivalence, I can give you the inverse. The thing is B lambda tensor. So given a module in category O theta in the block, you take the form from this Q to this. This is a module over, it's a right module over this endomorphism. Basically because you can compose with endomorphism of Q. So first take endomorphism Q to Q, then apply from Q to Q. Conversely, or in reverse, you can talk about given a module over this endomorphism algebra, if you put it on the right, then because the right module over B theta, you can take this tensor product. And this one will give you a module in category of theta. And the point is that this is a equivalence of categories from a block to exactly this modules over B. Okay, I think that is a good point to stop. Sorry, I still went somewhat over time. But this is how we connect to finite dimensional algebras. There is much more one can say about this particular finite dimensional algebra. In homological language, it's called quasi-hereditary. In module representation theory, categorical language, one called it highest weight category. But again, yeah, I would need one whole lecture to talk about that. So this is a good point to start with the recordings.
So thanks a lot, Apoorva. Yeah, for bringing everything together at the end. And people who want to see more about this should attend our next year's workshop. And then they will understand more on the role of quivers in representation theory and different flavors.
Right.
And
Finite algebras all come from quiver path algebras modulation.
yes, yes.